So this little simulation is rolling of dice. So here we have one dice, and we're going to be able to roll, like if I click on it, it rolls, right? So this is very tidy distribution, isn't it? So now, not so tidy. What is our expectation? 1, 2, 3, 4, 5, 6. Each of them, if it's a fair dice, would have the probability of 1/6. So we're expecting, and this is a new word, a rectangular distribution because it will be flat. But what I want you to notice, if I roll automatically, that it doesn't look very rectangular at this point. Okay, so when you're writing this up on your Google site, I want you to screenshot when you've done about 10 rolls, screenshot when you've done about maybe 50, screenshot when you've done more. So what we're trying to observe is the more times you throw the dice, and every time you throw the dice, the graph's changing because you're adding that one on. Do you understand? So it's becoming more and more rectangular. So the key idea is our simulation, which has given us a distribution of the rolling, that is getting closer and closer to the shape of the theoretical probability. So the theoretical probability is that each of these numbers on the dice would have the probability of 1/6. So the theoretical distribution is a perfect rectangle. But the actual distribution is a little bit more messy than that. So you can see there, it kind of looks like a rectangle, but it's quite a messy rectangle. And we've thrown the dice like 800 times. Okay, so that's one dice. Now, if we change that to 2 dice, just so we can change it to 2 dice here. And I just want to refresh it because I don't want to have thrown 1,000 dices. But can you see that that looks like a triangular distribution because it's like 2,000, right? 3,000. That looks like triangular. What does that remind you of that we did last week? The snails. Yeah, that's the exact same distribution. But if I refresh, all right, and then make it 2 dice, if I just roll, right, so adding to 3, that's adding to 6. You can see that if you, what was the winning snail? 7. Yeah, it was supposed to be 7 the most often. So here you can see in a short race that, 7 actually won that race. If you stop the race now, right, 7 would win. I'm just going to keep going. Oh, this is 7 is really well ahead. So the idea is that it looks messy when you haven't rolled a lot, but when you roll more and more and more, 7 is more and more likely to be the winner because it has the greater probability. So the more times you roll the dice, the closer it's getting to the theoretical probability. So the shape of our theoretical distribution is a triangle, but this is not a triangle, right? It's a messy triangle. So that's kind of the idea I want you to get. The next thing you can look at is 3 dice. So if I can move that up to 3, and what would you expect that distribution to look like? Now that's extra for experts if you wanted to work out the probability of adding 3 dice together and the shape of that distribution. But to me, it looks more like a normal distribution, which you might like to Google, than it does a rectangular distribution or a triangular distribution. So the normal distribution is a different curve altogether. So if you just go normal distribution and go to images, you'll see all sorts of images and things about the normal distribution. We haven't done it yet, but it's that shape. Otherwise known as the bell curve, which you might have heard about. Okay, so that's going to be next week, talking about distributions. And the dice is quite a nice way of looking at it. I wonder what that's going to look like. I reckon it's going to look like a normal distribution if we wait long enough. It looks pretty messy at the moment, right? Bit of fun.